So in lesson 1, we talked about the limit definition of the derivative and how to calculate some algebraic derivatives. And now I want to talk about graphs of derivatives, because once we've done both of those things, we can smash it all together and talk about it all at once. So that's what we're doing. So the limit definition of the derivative, when you want to find the derivative at any point, we often call f prime of x. I'm trying to find the right pen here. And f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h, provided that the limit exists, because some functions are not differentiable. So assuming that the limit exists, that's going to get you your derivative. So that means f prime is a function that represents the slope of f of x at varying values of x. And in our course, we often talk about the words derivative and the word slope being synonymous, basically. There are other notations for f prime. So we can have f prime of x. We can have dy dx. That's another way to talk about the derivative. Sometimes you'll see it written as y prime. I tend not to do that. I just don't like it. But dy dx and f prime are the two that you are going to see most often. And so if I want to create the graph of the derivative, in other words, the derivative for all the x values, I need to look at how f of x is moving. Because if f prime is the slope, that slope is telling you how steep f is and how it's moving when we look from left to right. So if f is increasing, if f is going up, I don't know which hand to do this in. Do I get mirrored when I make this? I'm not sure. But if I want to know how f is moving, and I know f is increasing, something that is increasing is going up. So f prime would have positive y values. Therefore, f prime would be above the y-axis, because if f is increasing, its slope is positive, which means f prime is positive, and the y values of f prime are what indicate the slope of f. If f is decreasing, then f prime would have negative y values, and f prime would be below the x-axis. If f has a slope of 0, if f is flat, it goes up and then it comes down, or it goes up, flattens, and keeps going. If f has a slope of 0, then f prime would have a y value of 0. Therefore, f prime would be on the x-axis. If f of x is getting steeper, either it's climbing and it's starting to climb at a real steep rate, or it's declining and it's starting to decline at a really quick rate, that means its slope is like positive 50 or negative 50, which means that it is very far away from the x-axis. Conversely, if f of x is getting shallower, then f prime would have y values that move closer to the y-axis, because if it's getting shallower, it's leveling out, its slope is getting nearer to 0, meaning the y values of the derivatives are nearer to 0, which means you're near the x-axis. Okay. So that's all about when f prime exists. When does f prime doesn't exist? So the derivative of f will fail to exist whenever, by the way, aka, that means f of x is not what's called differentiable. When f of x has a cusp or a corner. So let's say I take a function that looks like this. For example, f of x is the absolute value of x. Now, if I think about the absolute value of x, the slope on the left, the slope when x is less than 0, is negative 1. So my derivative would be negative 1. And then on the right-hand side, f of x is going up with a slope of 1. So it has a slope of positive 1. But right at 0, there's a corner. And how do I decide whether that corner has a slope of negative 1 or positive 1 or 0 or I don't know? So at the corner, the derivative does not exist. And in this instance, it means that I have a jump and 2 holes. Okay? What if f of x has a vertical tangent line? That happens more often than you would think. For example, I should do red, I'll be consistent. If I look at this graph right here, and this would be f of x is equal to the cube root of x. Right at 0, that has an instantaneous vertical tangent line as it tilts around. But a vertical tangent line would mean that the slope is undefined, and since slope and derivative are synonymous, that means my derivative is undefined. So if I were to graph the derivative here, the slope of this red graph is very shallow but positive, getting very steeply positive. So my derivative would look like this. And then on the right-hand side of 0, I start with a very steeply positive slope and get to a more shallow slope. So that's what my derivative looks like. So whenever f of x has a cusp or a corner, f prime has a hole and possibly a jump. Okay. And I want to say it's and always a jump, but I'm just not sure about that. So we're going to say and possibly a jump, but I'm pretty sure it's always a jump. And if f of x has a vertical tangent line, that means f prime of x has a vertical asymptote. What about if f of x has a hole? If f of x has a hole, then f prime of x has a hole. That one's pretty easy. So if I think about a function that has a hole, let's say something like this. When I go to graph the derivative of this, I meant for that to be blue. Blue, dang it. F prime of x would look something like that, and it would have a hole at the same x value as the original. So there's f prime, and the red one is f. And if f has a vertical asymptote, then f prime has a vertical asymptote. So let's say f of x is the function 1 over x. When I go to graph f prime, 1 over x on the left here is going shallow and downward and then steep and downward. So my slope is negative but near 0, and then negative but very far away from 0. That derivative actually looks very much like the original. It's not exactly the same, but it's really close. And then when I come over here, this is going downward again, very steeply downward to shallow downward. So f prime is really a reflection of itself on the right-hand side. All right. And then last but not least, f of x is like a broken piecewise function. So if I had something that looks like this, oh, red again. So let's say f of x looks like this, and then I've got like a line here, and then let's say I've got a curve here. Let's say that's some piecewise broken function of f, then f prime is going to be broken with holes. Okay. So if I look here, this is a horizontal line. The slope of a horizontal line is 0. So my first part of my slope is right there on 0. But then at whatever this x value is, the derivative doesn't exist because it's broken. This part of it seems to have a slope of 1, so then I'm going to have a slope of 1 for a while, but then it's broken again, so my derivative has another hole. And then this f goes from decreasing to increasing, so my slope goes from negative to positive, so my derivative goes from below the x-axis to above the x-axis. And that's what f prime would look like. Now, I drew those pretty quickly without really explaining much what's going on. So now let's explain what's going on. So it says each of the following is a graph of f on the same set of axes. Draw the graph of f prime. So I can do that. If f is this line right here, f prime is the slope of that line. Well, if I look kind of carefully at this line, its slope is up 3 over 1. So the slope of that line is always 3. So the value of the derivative is always 3 as well. That's going to be f prime of x right there, and it equals 3. Right here, I have a function f that is increasing and then decreasing, and right here at the top, the slope is 0. So when we graph the derivative, if we ever have places where we know the slope equals 0, I'll usually plot that point and say, okay, if my slope is 0 at x equals 0, that means 0, 0 is a point on the derivative. F is increasing, so f has positive slope, and then f is decreasing, so f has a negative slope. So my derivative needs to go from above the x-axis to below the x-axis, passing through 0. So here's the graph of f prime. Now, I'm not going to get into many specifics on this one about what exactly the graph of f prime is, because we'll deal with that more as we get into the derivative formulas and the derivative equations. So for right now, just know that that f prime is that line or something tilted like that. And then last but not least over here, I got a piecewise linear function, and I have 1, 2, 3 corners. All right, so if I have 3 corners there, I'm definitely going to have 3 holes in my derivative. So let's see, this first corner comes after a slope of -1. So my derivative equals -1 until that first corner. My next slope seems to be down 3, right 2. So my slope is -3/2 or -1.5 until we get to this x value. Then my slope is 0 from x equals 1 to x equals 3. So my derivative equals 0. And then my slope is up to right 1, so my slope is 2 from there on out. And there's f prime. All right, this one says, given the graph of f prime, sketch a graph of f given that f of 0 is 2. Why is it important that you have a point on the graph of f? Okay. Well, let's think about that. There's f prime. I'm going to try to sketch f. I'm going to use red now. Given that f of 0 is 2. Okay, fine. I'll start here. Why is it important that I have a point on f? I'm pausing to make sure that you're thinking too. Well, the reason that that's important is because f prime tells me about the slope of f, not the location of f, just its steepness. So there are an infinite number of what are called antiderivatives to every derivative. And those antiderivatives are going to be vertical translations of one another when we're talking about functions. So in this case, all I know is the slope. So right here, if that's the graph of f prime, I know that f has a slope of -1 and it has to pass through here. So I know that the beginning part of my f function looks something like that, and that slope of -1 continues to here. Okay, then I know that my slope changes from -1 to a slope of 2. Now, my derivative isn't continuous. They don't tell me whether f is continuous. So in order for me to draw the next part of this graph, I have a couple options. I could draw f with a slope of -1 and then draw f with a slope of 2 and make them connect like this. That would be fine. That's a perfectly acceptable graph of f. That f would be continuous, even though its derivative is not. However, since my derivative isn't continuous, all I know is that f went from a slope of -1 to a slope of 2. I could restart f down here, like end this here, restart f down there, and have a slope of 2. And I don't know which one it is. Okay, so that could move anywhere it wants to move, which is kind of interesting. All right, so why is it important you have a point on the graph of f? And it's because f prime only gives you the slope of f, not its current position. Okay. Sketch a graph of a function whose derivative is always positive, always negative, the same sign as the x coordinate. Okay, so if my derivative is always positive, then my function always has positive slope. So I need a function that's always increasing. Oh, okay, so if I want a graph that's always increasing, I could just make my life easy and just draw a line. Sure, I'm fine with that. I could also draw something that does something like that. That could also be a graph of f. Either one is fine. All right. A graph of a function whose derivative is always negative. So if the derivative is negative, the slope of the original is negative, which means that the original is always decreasing. Okay, so I want a function that's always decreasing. That's always decreasing. Cool. All right, then we get a little bit tricky here. A function whose derivative is the same sign as the x coordinate. So if the derivative is the same sign as the x coordinate, then the slope is the same as the x coordinate. So when x is positive, I want my function to increase. And when x is negative, I want my function to decrease. So I need a function that decreases and then increases. How about this? Wouldn't that work? On the left-hand side, when x is negative, the function is decreasing. Therefore, its derivative would be negative. And on the right-hand side, when x is positive, the function's increasing. Cool. Assume f prime of c is 3. Okay, in other words, the derivative at c equals 3. Fine. Find the derivative at negative c if f of x is odd or even. Ooh, okay. Now, if you remember, I'm going to talk graphically because we're in a graphic part of the unit. If f of x is odd functions are symmetric with respect to the origin. Okay, so if I want a function that's symmetric with respect to the origin, that would maybe look something like this. Like f of x equals some kind of a cubic function. And it says f prime of c is 3. So I'm going to say, what about like right here? Let's call this c and say at this c point, my slope is 3. Find f prime of negative c. So if c is here, then negative c is over here, and I'd be looking at the slope of that point. Now, I'm not so good at drawing these, but what you should notice is that they are both the same slope. If I have an odd function, f prime of c is 3, f prime of negative c, also 3. If I have an even function, that's a function that is symmetric with respect to the y-axis, say something like the cosine function, and f prime of c is 3. So now let's put c like over here. That'd be right there. That has a slope of 3. If I pick that same point over here, it's a decreasing, but with the same steepness. So f prime of negative c on an even function would be the negation of f prime of c. So just something to kind of push your brain a little bit. Now we got to think about odds and evens and how that might be helpful to us. All right. We have another page of this, but I feel like this is getting out of control already, so I am going to stop right here. What I want you to do at the end of this video is you are going to click on a link and do an activity to see how much you understand so far. Okie dokie. So I need to give you a joke. The joke today is going to be, what has 8 eyes and 8 legs? A spider would be correct, but the joking answer of that is 8 pirates. Because they have a patch and a peg leg. 8 eyes, 8 legs, 8 pirates. I hope everybody's having a good day and you continue to have a good day, and I'll talk to you soon.